carry loads primarily in the first of these, the ring compression methodology or mode. Ring bending strength is primarily used during construction, during the handling of the pipe, and during the backfilling of the pipe. After the embankment is in place and supporting the pipe does carry load primarily through ring compression strength. And to just kind of illustrate this, I think if everyone at some point or another has or at least can picture kind of an old coffee can, it's a relatively flexible ring that if it's unsupported, if you're just holding it in your hands, you can probably flex it with your fingers, and certainly if you stood on it or drove a car over it, you would probably flatten it. But if you then surround it with a supporting layer around it that can help control the deflections, then it can actually carry considerable amount of load. And certainly we could drive a car over it, or you could stand on it. And that's really what the basis of the ring compression theory and the structural design of corrugated steel pipes is all about. Having that support for the ring around it being provided by the earth embankment, and thereby allowing it to carry loads through compression in the pipe wall, as opposed to bending within the pipe wall. So the design procedure, I'm just going to kind of step through and give an example of a design for a flexible pipe. The one I'm going to give is actually for structural plate, but I did that primarily because structural plate has seams, and there's a seam strength check that goes along with that. Obviously, a lot of corrugated steel pipes that are continuously made and don't have any seams, that they skip that step, but I included it today just to illustrate that particular check. And so the example I'll be giving today is for a structural plate structure. But the first step is always to determine the pipe properties. So the pipe properties are available from a number of sources. The one that again we use primarily is from the NCSPA design manual. The same manual that has the design methodology that I'm going over today also contains all the mechanical, sectional properties, seam strength properties, and flexibility factors that I'll be utilizing in the design methodology today. So a lot of these properties are also contained in ASTM and also in AASHTO standards as well. So for this particular example, I'm going to be going through a structure that is comprised of a 6x2 corrugation profile. So it's a 6-inch pitch and a 2-inch wall depth for the continuous sinusoidal corrugation. This is a 25-foot diameter structure, so it's a round structure. It has a 1-gauge thickness, which is just over a 1/4 inch thick. And the wall properties that you can see below there and the mechanical properties are all taken from the references that I provided earlier in terms of the wall area that's available, the bending strength, the moment of inertia that wall profile can provide, the radius of gyration, modulus elasticity. Of course, this is a steel material, so it has a modulus elasticity of about 30 million psi. Yield strength is 33,000. That's standard for the industry. Tensile strength, and then the seam strength for this particular structure, with a 4 bolt per foot pattern, which would be standard, is that 144,000 pounds per foot value. But anyway, all of these values are available in the design manual, and this is what you would gather first in order to perform the rest of the design check. So the next step would be to determine the compressive stress that's acting on the pipe wall. So in order to do this, we need to first accumulate what the loads are that are being imparted on the buried pipe. So that's really broken down into 2 different categories. There's a dead load, which is really just the overburden pressure of the weight of the column of soil that sits directly above a vertical projection of the pipe itself. The weight of that soil is considered the dead load, and then the live load is typically your vehicular loads. So whatever you might be designing for, if it's a standard highway, you'd be using a standard highway load. If it's a railroad application, you'd be using railroad loads, airport loads, etc. So typically the way the dead loads are computed, and you can kind of see that illustrated on this slide. This particular structure has a height of cover, assumed height of cover of only 3.4 feet. The unit weight of the soil is 120 pounds per cubic feet. And there is in the NCSBA methodology, there's a load factor that is available. It's a K factor. Essentially, what this recognizes, this K factor is intended to recognize is that for deep burials, and deep burials are considered any amount of cover that is in excess of 1 diameter of cover over the top of the structure. So this is a 25-foot diameter pipe. So if we had 25 feet of cover or greater, this K factor would be a factor that's slightly less than 1. In most cases, it depends on the stiffness of the soil that's being used, but in most cases that factor would be 0.86. Which means we would be applying a 14% reduction to the overall dead load that's being imparted on top of the structure. That's really just recognizing that you do get some soil arching if you have an appreciable amount of cover over the top of the structure. In this case, we've only got 3.4 feet of cover, so we are imparting the full dead load weight of the soil column over the top of the structure. So you can see here that the dead load numerically is just the 120 pounds per cubic foot soil density times the depth of fill over the top of it of 3.4 times that K factor of 1. So it's 408 pounds per square foot of dead load that's being imparted on the crown of the structure. The live loads are typically taken from tables, such as the one that's illustrated on this slide. So for standard highway loads, railroad loads, there are various tables that are available that will allow you to just kind of pull off what the live load pressure is exerted by various vehicles. Again, these are available in the NCSBA design manual, and in this particular case, assuming that this was an H20 vehicle, the live load pressure is 600 pounds per square foot. And so then the total load that would be acting upon the crown of the structure is just the sum of the dead load and the live load, which in this case is just over 1,000 pounds per square feet. And then to change that load into what the stress is in the pipe wall, we just use the equation of multiplying the overburden pressure by half the span. That yields what the ring compressive force is, or in some cases it's called the thrust that's being imparted on the pipe. So in this case, numerically, it's 1,008 pounds per square foot times half the span. It's a 25-foot span, so half of that would be 12.5 feet. And so the force that's acting on the pipe wall is 12,600 pounds per lineal foot of pipe wall. And then taking that load and dividing it by the wall area available, that would give us what the average wall stress would be, which in this case would be 3,059 pounds per square inch average wall stress that's being that this pipe is being subjected to. So that's always the first step, is computing what the stress is in the pipe wall. The next step would then be to determine what's the allowable stress. So now we've computed what the actual stress is. Now we would determine what the allowable stress is on the pipe wall, and this would be there's a formula within the NCSBA methodology, essentially that is all based on a ratio, kind of a slenderness ratio. It's the span divided by the radius of gyration of the pipe wall. Essentially, the reason that we do this is because depending on the ratio of the slenderness to the slenderness ratio of the pipe, As pipes become more slender or larger structures with with smaller radius of gyration available, pipes will either fail in compression. If you kind of remember back to the old Euler buckling formulas, buckling was always based on a L over R ratio, which again was called the slenderness ratio, and it kind of fell into three camps. For structures that were very beefy, in other words, they had a lot of compressive capacity and they would have a very low slenderness ratio, those would fail just through axial compression. So essentially you would take the yield strength of the material, divide it by a factor of safety, and that would be the limiting stress that would be allowed. As structures become more slender, so this KL over R ratio or this span over radius to gyration ratio in this case for pipes, as that gets larger and larger, you go into a buckling mode, which will control what the allowable stress would be. And so in this case, you can see that the slenderness ratio is a value of 431.7. Well, that falls within a range of 294 to 500, which means that that's an intermediate buckling phase. So the formula that you can see below that would be applied in order to calculate what the allowable stress would be. If the slenderness ratio falls above 500, there's a different buckling formula that's a long column buckling formula or some derivation of that. But anyway, as you go through the methodology, you take the slenderness ratio, you figure out which buckling equation yields the appropriate allowable stress, and then you would check that versus the actual stress that we computed in the earlier step. So in this case, the allowable stress is 12,453 psi. The stress that we computed was actually acting on this pipe wall was 3,059. So therefore, the allowable exceeds the actual stress, and so we're okay. So the next step would be to check the handling and installation strength, or sometimes called the flexibility factor for the pipe. So for all pipes, there's a certain amount of bending strength that is required. That's really where this comes in with the flexibility factor. Essentially, there's a minimum pipe stiffness level that is recommended depending on the corrugation and the shape of the structure that you're utilizing. So we do go through this as a additional check. It is called the flexibility factor. In the metal pipe industry, essentially there is a limit. The number that's in blue on the screen, this 020, is the maximum limit that would be allowed for this particular structure. The flexibility factor is computed by taking the square of the span and dividing it by the stiffness of the corrugation profile, which in this case is just EI. And so numerically, if you go through this, you'll see that the actual flexibility factor of the 25-foot diameter 1 gauge 6x2 structure that we're talking about numerically is 0.018. The allowable flexibility factor limit is 020. So therefore, this combination checks and it passes the flexibility factor limit. The next step would be to check the seam strength of the pipe. And again, I have on here if applicable, because again, if a structure has a continuous lock seam construction, then there is no seam, and so there's no seam strength that is necessary. But for bolted structures, such as a corrugated structural plate structure like the one we're talking about, or a riveted pipe, then the seam strength does need to be checked. The seam strength that's required is simply the thrust or the load that is on the pipe wall that we computed earlier, multiplied by a factor of safety, and then compared to the seam strength limit for the pipe that we have. So again, the thrust load that is acting on this pipe was 12,600 pounds per lineal foot of pipe wall, multiplied by a factor of safety of 2 means the required seam strength for this pipe would have been 25,200 pounds per lineal foot. We compare that to the actual seam strength that 1 gauge 6x2 provides, which is 144,000 pounds per lineal foot. So therefore, this check is also okay. And then we also want to check the minimum cover required for the pipe. And the minimum cover is again provided by the design methodology, and it does depend again on what the loads are that are being imparted on it. Essentially, for the corrugated steel pipe industry, for highway loads, for standard highway loads, the minimum cover is the span divided by 8, no less than 1 foot. For this does vary a little bit by there are some corrugation profiles that have a different limit. So the spiral rib profile has a limit of span over 4, not less than 12 inches. And minimum cover is always measured from the inside rise of the pipe to the bottom of an asphalt pavement or to the top of a rigid pavement. So that's how minimum cover is evaluated. And again, for E80 loads, there's a different minimum height of cover limit required. So usually it's 2 times whatever is required for highway loads, or for structural plate, it's a span over 5, not less than 2 feet. And then for aircraft loads, again, there are tables that you can go into depending on the size of the airplane that's being designed for. You can look up what the minimum cover requirements are for some of those aircraft loads. And then the last check would be to check the corner bearing pressure for a pipe arch. Now, the example I'm going through is a round pipe, so a round pipe this would not be applicable to, but if it were a pipe arch structure, for pipe arches, there's one additional concern that needs to be looked into, and that is the corner pressure that is exerted. Multi-radius structures can exert a pressure on the soil beside them that is higher than just what the overburden pressure over the top of them is. So essentially, to check the corner bearing pressure for a multi-radius structure, you just take the overburden pressure and you multiply it by the ratio of the top radius, the large top radius, to the smaller corner radius, and that pressure needs to be lower than what the soil embankment can provide in terms of support. Typically, that value is anywhere from 3,000 to 4,000 pounds per square foot, but of course it could change depending on your site conditions. But that check only needs to be applied for multi-radius shapes. The example we were going through is for a round structure, so that would not apply in this case, but I did want to highlight that just in case. And then we talked before about everything we've been talking about is ring compression structures, the design of ring compression as the methodology by which all of these structures are designed. But we talked about the fact that the bending strength, is also important for the pipe wall. And we talked about that a little bit when we were talking about the flexibility factor. Again, that there's a minimum stiffness that is required for these. And, again, that bending strength is primarily required during the handling of the pipe as it's being, either loaded onto trucks, unloaded off of trucks, assembled and then lifted into place into a trench. Also during the compaction, the construction of the embankment around the pipe, those compaction loads will impart a lateral load into the pipe, which can deform it if it doesn't have enough inherent stiffness on its own. But after you get the fill placed on top of the, around, completely surrounding the structure and up to that minimum cover. After you get that amount of soil support around the structure, then it does start to act in ring compression, and the bending strength of the pipe at that point is generally inconsequential to its performance in the field. Again, this is all for the only exception to this for corrugated steel pipes is for deep corrugated profiles. In those cases, ring compression theory doesn't apply, and we actually go through a finite element methodology in order to evaluate those structures. So you can't use the methodology that I just provided for deep corrugated structures, but it does apply to everything else. So, and it just got a few photos here to kind of illustrate why the inherent stiffness of the pipe itself is important. You can see here a pipe that has been assembled and is being lifted into place. Obviously, you want to have enough stiffness inherent in the pipe itself that it doesn't deform during the handling and installation process. Also during backfilling, we talked a little bit about, as you're building that embankment next to the structure, there's going to be compaction equipment that's going to be imparting vertical loads to densify that material. Those vertical loads also have a lateral component that will tend to want to distort the structure during construction. So again, you need to have the inherent ring stiffness and bending strength of the pipe wall profile to resist those deformations. But then once you get structure up over the top of the structure to the minimum cover level, then the pipe will then act as a ring compression structure, and again can carry very high heights of cover or very large vehicles, such as shown in the mining equipment crossing over this structure. And of course, you can go through all that methodology, and that is what is the long form that is used, by the industry. But the good news is that you don't typically have to go through that level of detail, because there have been height of cover tables that have been developed for really every corrugation profile and gauge that is commercially available within a number of different industry publications, including the NCSPA design manual. So what's shown in this slide is a height of cover table. You can see that it shows the height of cover limits for a 2 2/3 by a 1/2 inch corrugation profile. You can see that it shows what the minimum cover by diameter. Diameter goes down the left side of the table. The next column over shows what the minimum cover for each of those diameters are, and then goes through the gauge thicknesses that particular pipe would be commercially available in, starting from the lightest gauge, which would be 16 gauge, over to the heaviest gauge of 8 gauge, which is shown in the column to the far right. And so you can just go down whatever diameter you're interested in using, and then go over to whatever gauge thickness you're planning on using, and you can see what the maximum cover limit is that the pipe would be able to carry. And there's tables just like this for every commercially available profile that's out there, again with the exception of deep core structures, because those do require a finite element analysis in order to determine their structural capacities. So that's the LRFD, or I'm sorry, the NCSPA methodology that's simplified. I did mention that another widely used design methodology is the AASHTO LRFD methodology. And again, the two methodologies are very similar, so I didn't want to go specifically step by step through it, because essentially they are identical in terms of the checks that are performed. But there are some differences. So really all I wanted to do is use this slide to go over what some of the differences are between the two design methods. So the primary difference is that the NCSPA method still uses allowable stress design. So we talk in terms of factors of safety. And so we'll apply factors of safety to the design limits. such as the seam strength values, or the yield strength would have a factor of safety applied to it to get down to what the allowable stress would be. The AASHTO LRFD methodology, LRFD stands for load resistance factor design. So it uses load and resistance factors to essentially get to the same end goal, which is to make sure that there is a sufficient amount of excess capacity within the structure to safely handle the service loads that it's going to be seeing. So one uses a load and resistance factor methodology for determining what the the performance limits would be. The other applies an allowable stress factor of safety approach. The checks performed are very similar between the two methods. They're really identical. There is some small differences in terms of the equations that are used for, say, some of the buckling formulas, but they're very, very similar in terms of the results that they provide. And the checks are the same. You still go through the same step of checks. There are some minor differences in terms of the flexibility factor limits. Again, they're very similar, but there are some small differences. And probably the most significant difference in terms of performance is in the seam strength requirements. So the traditional NCSPA design methodology only requires a factor of safety of 2 on seam strength. AASHTO for years and years has required a factor of safety of 3 on seam. So that's probably the most significant difference in terms of methodology between the two. And there is no NCSPA design methodology available for deep corrugated structures. Again, we talked about those are not ring compression structures, and so they do require a finite element analysis for those. And then how does this affect the calculations and the height of cover tables between the two methodologies? For the most part, they're very similar. If you go through in case by case and look at them, you'll see that the maximum covers will decrease slightly between, and they'll be slightly lower for the AASHTO LRFD methodology. That's essentially because if you kind of take the result of the load and resistance factors, you'll see that there is a slightly higher kind of equivalent factor of safety that's applied by AASHTO as compared to the NCSPA method. We're talking about 2 to 3% difference in most cases, so it's certainly not significant, but that is one difference that you would see. And then in terms of minimum covers are essentially the same. So there's really no change between the AASHTO methodology and the NCSPA methodology. And so with that, I'm going to turn it over to my associate, Eric Early, who's going to talk us through some of the other aspects of structural design for corrugated steel pipes.
Thank you, Daryl. Good afternoon, everyone. As Daryl has said, my name is Eric Early, and I'm a design engineer at CONTEC. Daryl went through the structural design procedure for what I'd call a typical corrugated steel pipe. I'm going to kind of touch upon the remaining design considerations and special applications that exist for other variations of corrugated metal pipe and plate. So the first object is finite element analysis. So as Daryl pointed out, he said that the NCSPA does not have a design methodology for deep corrugated steel, which is correct. However, if you reference AASHTO, it requires the deep corrugated steel structures to be used with a finite element analysis, or FEA as it's more commonly known as. So the FHWA, the Federal Highway Administration, developed a finite element analysis called CANDY, which is short for Culvert Analysis Design. And I have put a couple screenshots on this slide where the top right, you can see a mesh for a round pipe, and then the bottom right is a bending moment graph that's spit out. So this models and analyzes the culvert, the surrounding soil, and the live load interaction specifically for buried culverts. So in this illustration, you can see there's many different colors in that mesh in the top right, and this depicts the various different soil types. So you have your in situ material that you input, you have a select backfill material, you would also add a live load. In this program, it's a complex model of elements and nodes with all site-specific user inputted parameters to help you verify a structure gauge or foundation reactions in the event that it's an arch. So now I'm going to touch about backfill briefly. And earlier in this, it was mentioned that corrugated steel pipes designed based on a termed a complex soil structure interaction. So thus the backfill material is very critical. And it can vary depending on how large of a diameter you are, or what if you're using, say, a pipe versus a plate product. So I'm going to slightly get into a little bit of differences. So the quality of the backfill material is defined by the soil stiffness, which is the result of the soil composition and the level of compaction. Well-graded, clean, non-plastic materials, they compact more easily. The optimum moisture content is easier to compact, and you'll notice that you'll have an angular material that'll help eliminate void spaces throughout. So with that, non-plastic sands and gravels are considered the best quality material. This is referenced as like an A1 material per AASHTO M145, which we'll talk about on the next slide. It is possible that material from the job site, the in situ material, may be suitable. This would have to be evaluated on a case-by-case basis. Organic soils or peats are unsuitable, and some soils with some plasticity are acceptable in some cases, and that's limited really in the AASHTO M145 methodologies as well. Once you get into higher fills, you're worried about the soil load being carried because it's affected by the quality and stiffness of the backfill. So if you have a lesser backfill material, you will generally have less stiffness that's being carried down and help being transferred around the pipe in ring compression. So better materials help reduce the loads on the pipe while also providing better support and improving the structural strength. Another aspect of flexible pipe is that it's designed to carry the full soil prism above the pipe, while concrete or rigid pipe may not consider the entire prism above the pipe. One thing to note is compaction to 90% standard Proctor density is generally sufficient, so that's AASHTO T99. And that is more so on the pipe side of the business. Once you get into larger plate structures or deep corrugated structures, you might need to compact to 95% or 90% per AASHTO T180, which is modified Proctor. So the last note I want to say is that AASHTO requires backfill to be an A1, an A24, an A25, or an A3 per AASHTO M145. And on this following slide, which you can now see, this is a chart comparing the two common soil classification systems. So you have the United Classification System, UCS, on the left, and AASHTO M145, more so in the middle of the table. So the UCS is based on a system where G stands for gravel, S sand, M silt, and C is clay. So everything that is A3 and above on this is considered a granular material, and that'll have 35% or less passing the number 200 sieve, and everything below that, so an A4 through A8 would not be subject for backfill with these corrugated metal pipes. These are silt clay materials where they're passing the 35% sieve with more than 35% passing the number 200 sieve. So in the A1 group, these are the well-graded gravel or gravelly sand. So these are that non-plastic angular materials and gravels that are the ideal backfill materials for a job site. Also for the plasticity index, per AASHTO M145, the A1s can have a max of 6 for the plasticity index, and typically the A24, A25 will cap it around 10. So you can have a little bit of plasticity, but ultimately you're trying to limit that. So that is the backfill design portion. We'll go into more detail in the next webinar on installation. So there will be more talk on lift sizes and installing the pipe, as well as the backfill procedures that lead up to that. And that'll be presented by both Mike McGough with NCSPA, who is capping this one off, and Mark McCord from Southeast Culverts. That is next Thursday, or sorry, 2 Thursdays from now, June 11th at 2 p.m. So end treatments. End treatment design, you have to consider hydraulic forces, which can cause erosion of the backfill material. It can damage the structure, or it can inundate the bedding. So proper backfill placement around the structure ends is critical to try and eliminate any potential erosion. And also another consideration would be aesthetics. Sometimes that's not as big of a concern, once again, with smaller pipes, but if you get into a larger plate product, say in a subdivision, you might have some concern about aesthetics, where you might want to put a nicer facade on a wall. So a few of our options, as you can see on the left there, we can do projecting square ends. So that is just a typical structure. There's no cutting involved, and it's recommended for most pipe applications. The structure has to be long enough to allow the toe of the slope to meet the invert of the pipe, so you will have a little bit of a protruding edge sticking out of the soil. Then there are a couple bevel considerations. You could do a full cut, so that would be cut from the crown diagonally all the way down to the invert. So this will improve the structure aesthetics and hydraulics by removing the excess metal, but it's also not recommended for pipe arches because you're losing a lot of stability at the bottom of the pipe. So a step bevel is preferred, and that is, there's a picture of that in the center of the screen here. We try and limit that to a 1.5 to 1 or a 2 to 1 range, because you get a little bit more stability, but you're still cutting into your pipe, so you're losing a lot of your strength there. Another option is a skew cut. So in the bottom center of the screen, you might want to skew your pipe to match the skewed roadway. Instead of having it stick out an extra, say, 10 feet on one side, you can cut it to length to match your roadway. But when you do this, you need to be certain that you're extending the toe of your slope out to prevent unbalanced loads. So on the top of that image on the bottom, you can see that the soil is not evenly on both sides. So you're going to have excess forces on one side of the pipe that you're not going to see on the other, and there'll be some unbalanced forces. So with that, one big thing to point out with these end treatments is the strength of corrugated metal pipe or corrugated metal plate is in the longitudinal direction, so across the corrugations in ring compression. So anytime that we're cutting a pipe for a bevel or a skew, ring compression is interrupted and the pipe becomes limited to the bending strength of the corrugation, so you lose a lot of your structural capability. And due to this, we advise that you use either a concrete collar or a head wall to help reinforce the cut areas. In some cases, before your collar's complete, if they start wanting to do backfill, you may need to put a temporary brace on this until the collar's complete to prevent distortion. So here's a couple of images for end treatments, just to give you a wider array of what all is available. Since we're going to be a little bit short on time, I'm not going to touch on this too much, but you can see the bottom left is a full bevel, and just looking at how much of that pipe is cut off, you can see that you're losing a lot of your strength there. We also have images for flared end sections, for keystone head walls, for metal corrugated head walls or wire wall. There's a lot of options out there. So special applications. First, we'll go into fittings. So standard or custom fittings can be shop corrugated or shop fabricated with corrugated steel pipe. It's similar to the pipe itself in the way it's designed, in that the thrust of the fitting depends on the diameter and the loads. All reinforcement should be designed with ASTM A998, and there is a table in the NCSPA design manual that references maximum diameters that don't need reinforcement for up to 10 feet of cover with standard highway loads. So as the fittings get larger, or if you bury them deeper, You're going to have additional thrusts, which will likely cause you to have additional members to reinforce the main line. And this is similar to, as we just talked about, once you're cutting any of your corrugations out, you're losing a lot of your ring compression, and causes a lot of strength to be lost in the pipe. So adding some reinforcing members can help there. One way to avoid the amount of reinforcement you use is to use a manway, which is shown in this top right image. So it's a narrow doorway that's cut just large enough for a human to walk through there. This is really only applicable for structures for storage and not for flow, but this will help you reduce the amount of reinforcement. For bulkheads, this is essentially a metal sheet or end cap that's typically continuously welded to CSP. It might be field bolted or field welded to structural plate, and this also varies with diameter, cover, plate thickness, as does fittings. So it acts as a fixed edge diaphragm, and during fabrication, reinforcement must be on the outside to make sure it's in bending tension. And typically the bulkhead, plate, and reinforcement will always need to be adequately welded together, just to make sure that there's enough composite action. So this could be done with both angles or channels typically. CSP manholes, there's two common types of manholes. There's the riser type, which is shown to the right, and there's the shaft type. So the riser type is probably a little more typical, where you have a main line, larger diameter, and there's a smaller riser on top. Typically it's aligned with the spring line to help transfer loads, and it also helps allow a smooth transition to the floor with an access ladder. Reinforcement at the connection must be considered, so we're also following ASTM A998 there. For a shaft type, it's typically set with an open bottom, and you pour a concrete base slab on it. So this may only experience active soil pressure rather than the full soil prism load. And due to this, it could require less reinforcement than the riser type manhole. But when considering reinforcement, it still needs to be checked with ASTM A998. A couple of things to point out is there's typically a manhole cover or lid on this, and it should not rest directly on the CMP riser. We would recommend that a manhole be supported by a concrete cap, or essentially a footing that would rest above the top of riser, and make sure there's not a connection between these 2 points to eliminate traffic loads. And also drag down loads should be considered. So anything that you have over 10 feet of cover, or if you have poor soils, there can be soil settlement, and as the soil settles, it'll attempt to pull down the riser. So you want to prevent that by using a slip joint, which is a special modified band. So I'm going to go through these pretty quickly since it looks like we're running out of time and Mike still has a bunch to get through. So hydrostatic buckling, it's basically referring to pipes that are not buried, not compacted. So you're going to see a lot of pressure, and this is the majority of this pressure when you have uneven loads, say in a pond riser. It's going to be at the base of your structure. So if you embed this in a concrete slab, it helps eliminate some of the pressure. For vertical shafts, they're used to use construction pits, deep foundations, temporary casings. Once your shaft is higher than the water table, the shaft must carry the full hydrostatic load of water plus the active buoyant water force. So you need to take into consideration your active soil, hydrostatic pressures, and potential construction loads. Safety factors for buckling and seam strength for vertical shafts are 2. So relining, CSP is widely used for reline applications. That you can manufacture it in any shape or diameter. It's a quick install. We're going to have another NCSPA webinar in several weeks, I think August 6th, where we'll touch on this a little further. So it must be known that we typically reline or conservatively design relines to carry the entire load, but you do allow for a less stiff liner based on having a host structure, and just make sure that the grout must be distributed equally so there's not any uneven backfill. Reclaim tunnels. One of the items that Daryl had talked about was a load reduction factor, which was K. You're not allowed to use that since it's a cyclical loading where the ore piles go up and down. So in this case, you're going to be a little bit more conservative than you would if you use a K factor. So hopper openings, they require more significant reinforcement than just using A998. We would need to typically design to carry the bending moment developed in the longitudinal reinforcement due to the thrust of the pipe. So that is slightly different, and you might see some, or you're traditionally going to have some circumferential reinforcement as well. One thing to point is we should try to avoid hanging the hopper or conveyor directly on the pipe. So I'm going to skip my conclusions just to give Mike a little bit more time, but I will turn this over to you, Mike, since you got quite a few slides to get through with a little bit of time.
Thank you, Eric. No worries. So, gang, just to wrap things up, how are all of these applied in state form, right? So Daryl shared the tables that we had developed, the AISI tables that we've developed, and all of those, again, they're available in Chapter 7 of the Corrugated Steel Pipe Design Manual. I'm gonna look at a couple of state examples just to highlight how they've implemented this. So this is from VDOT. So VDOT has, again, developed tables just like we did, implementing, this is LRFD HL93 loading. So what I'm going to do is at the end of this presentation, I'm going to work through a couple examples, and that's why I highlighted these boxes here. So I'm going to work through a 48-inch diameter 14-gauge pipe, and as you can see, VDOT allows 71 feet maximum fill height over that pipe. And then I'm going to walk through a 72-inch 3x1 corrugation 14-gauge so the maximum height is 53 feet on that particular pipe. Similarly, Caltrans has a table, again, very similar. So looking at those same two pipe, 48-inch 14-gauge is 58 feet, and a 72-inch 3x1 is 44 feet. So as you can see, as Daryl said, there's some small differences, but 10, 15 feet when you're getting that high, we'll show you how to work through the calculations and why those differences are where they are. We touched on coatings last week. So just a quick recap. 3 primary coatings with the post-applied coating: galvanized, aluminized, and polymer. At the end of the day, guys, when we're doing structural calculations, the coating does not matter. So everything that we're presenting to you today is coating independent. This all applies to whether it's galvanized, whether it's aluminized, whether it's polymer, whether it's asphalt coating. The only thing that those drive, again, as we talked about last week, are the materials life dependent on the environment. So just to make that clear for everyone. Now let's head into some examples. Again, the website is where we're going to work from. We've talked about the design manual a number of times already. You can download that as a PDF to look through. It's 600 and some odd pages, and it really, the design manual encompasses everything that we're going to talk through in the webinar series. So just kind of keep that in mind. Now, the website, Daryl showed you a quick shot of the homepage. What allows you to do is this is a find a project page. So if you're looking for some projects around the country on different coatings, different applications and such, under the newsroom, you can see that. Let me turn my pointer on. So under the newsroom, which is in the top right, you'll find a project drop down, and that'll take you to this particular page here. And then when you highlight over the bubbles, it'll give you some of the project specs. And then, of course, you can click on the project itself to get more detail on each. So what I'm going to wrap up with is, how do you do this off of our website? So we have a corrugated steel pipe LRFD height of cover calculator. It is located here, this top right button. There's also an app. So for those of you that are app fiends, it's available also at the Android store and in the Apple store. And this is what it looks like. So there's really just some basic information to enter, and then it runs through the calculations for you. So similar to what Daryl talked about, all you're entering is diameter, corrugation profile, and gauge. All of this information is plucked from AASHTO, and we'll get to that in a second here. Once you select that, you hit the calculate button, it will give you your results. So 64 feet with a 1 foot minimum height. Now we go back, if you remember Caltrans in Virginia, they were at 58 and 71. So this falls right in the middle of those. Now, how can we tweak this, right? So we have all of these load resistance factors here, and that's what determines this. They are, again, they're derived directly from AASHTO, and here are the references. So similar to what, again, Daryl referenced for the AISI methodology, this is what we're applying here. Dead load factors, live loader factors, redundancy factors, a multiple presence factor, you have a density of the cover and a soil stiffness factor and a wall buckling. So this wall buckling is what takes into account the seam strength. Now, with one small tweak, we change the soil density from 0.120 to 0.125. It changes the height of cover, just a couple of feet. So if you continue to do that, small tweak, you change it to 115, it increases the soil. So you don't have as much dead load over top of the pipe with a denser soil, and that's what accounts for that. So moving forward, here we are. Second example, 72-inch, 3x1, 14 gauge. Gives you 49 foot of cover. Now, why do we have to move to a 3x1 profile? So this goes back to what Daryl was talking about with the flexibility factor check. If you were to do a 2 2/3 by a 1/2 inch profile at that diameter with that gauge, you really wouldn't be able to handle it. It would pop the lock seams, and it would pretty much just be difficult to move. So what happens is when you move to a 3x1 profile, it allows for better handling stiffness, basically. Now, real quick, just a couple other buttons on the site. There's an option to review results, and then there's an option to view the sample calculation. So when you're viewing results here, guys, all this is showing you are the variables that are, again, pulled from table A12.1 and A12.9 within the AASHTO LRFD bridge spec. So again, similar to what Daryl walked through for AISI methodology, you have pipe wall area, moment of inertia, radius of gyration, modulus of elasticity, the yield strength, the tensile strength, and then you have this flexibility factor that you have to account for. And then it will also lay out the contact widths and lengths, design truck width, and spacing for the HL93 truckloads, whether they're single trucks or whether they're tandem trucks. So that's all accounted for, again, with what we've encompassed in our calculator. And then the last button is you can actually view an example. So this is a 48-inch 2 2/3 by 1/2 14 gauge pipe. If you view the example, it will walk you through all the checks. It'll show you the pipe. It'll walk you through developing the pressures, live load and dead load. It will do the thrust calculations, the critical buckling check, factored axial resistance, and check the flexibility factor all for you. And then you can print this out and look through it. It shows you the mock-ups of the wheel pass and the depths and the impacts it has from the cover. As you can see, just, the load dissipates as you go further down. And that's pretty logical. I'm going to stop there, gang. Thank you for attending today. We're going to have a few more coming up over the next several weeks. So we appreciate, you guys joining in on those two. More specifically, our next webinar will be June 11th, 2 p.m. Again, that's going to be on installation offered by myself and Mr. McCord with Southeast Culvert. Again, we can turn it over to the chat room and I guess answer any questions that might be out there. What type of coating do you recommend for high abrasions and acidity? Asked Edgar. Edgar, that's so polymer would be your coating of choice in that particular case. Neither galvanized nor aluminized type 2 would work in that scenario. Well, I think that's it, everybody. Again, appreciate you joining. Have a great day.